Hello students, I am Dr. Tanmoy Vishwas. I welcome you all in my channel Chemistry of Molecule. So today we will discuss the properties and reactions of pyridine N-oxide. This is a continuation lecture of the previous video where I have discussed the preparation and the basic idea about pyridine N-oxide, and where I have discussed in details about aromatic electrolyte substitution, nucleophilic substitution, electron distribution pattern of pyridine N-oxide, and compared this with pyridine derivative. So that is very useful for understanding the basic part. So I request you, if you haven't watched that, please visit that video first. After that you come here. It will be helpful for your understanding, because those things what I have explained there, I am not going to explain in details here. So please visit that video. Based on previous day's discussion, we can conclude that if you take pyridine N-oxide, this is the pyridine N-oxide, and react with an electrophilic reagent, so what I have expected that electrophile will attack this 4 position or para position. But instead of that, if you do the reaction using, it's an electrophile, this is a nucleophile, means this, so expected it will be attacked on this 2 position, this thing, mainly because of that this off position 2 effect works. Actually, one is minus I, another thing minus R, and for this aromatic electrophilic plus R effect works, not minus I. So that is the advantageous for getting this. So in this way we can get 4 substituted pyridine. This is where you can get 2 substituted pyridine, and by direct aromatic electrolyte substitution on pyridine will provide the 3 substituted pyridine. So these 3 part I believe you must remember. So if you can remember this, it will be very easy in order to predict that whatever will be the product, because it is always not possible to memorize everything. But if we have a common idea, means a basic understanding, then if we don't know the question also, then we can solve, and this information will be helpful to improvise your basic understanding. So now let's go to the examples. Okay, let's discuss these problems. These 3 sets of problems. So we will now discuss about the pyridine N-oxide. So what happens if you take pyridine N-oxide and react with this concentrated sulfuric acid and nitric acid, which is known as mixed acid? What it generates? It generates the NO2 plus as the electrophile. Okay, and that react. Now question: if you want to see, just I told pyridine N-oxide is para-directing, fine. But for aromatic electrophilic substitution, for AES, mainly, so methyl, ortho and para. Okay, and another is meta with respect to this. So what is the purpose of this problem? This purpose of this problem is to provide you the selectivity of this process, that how much selectivity and how much strong contribution of this group. Okay, so that is the reason why nitrogen happened at this position. Okay, so the contribution of this is higher compared to this, because if you consider the methyl group, it's preferred to have para position, but here it is this position. Okay, so it means the contribution is more anti-selective. Okay, fine. So similarly, if you take bromine and thallium acetate, what is the role of thallium? Thallium acetate means a thallium 3, and it is in the aluminium group. So this thallium 3 plus act as Lewis acid. Lewis acid to generate the electrophile, because it takes the Br minus and generates. So if you react with Br, so what happens? It abstracts the Br minus and generate the. Better to say it's not in this way. That will be little illogical. Better to say that this Br it coordinates. So here delta positive generated, and this center act as the electrophile for the bromination at this position. Okay, so bromination happens here. Fine. Now the next problem. Next problem, see, it's a 4-nitro derivative. I have discussed this thing in the previous video also, but different example. Here I have taken acid. Okay, HBr or HCl. So first of all, when I take acid, it is expected that this will be protonated. Fine, first point that it will be protonated. Okay. Second point, what is expected when it attacks? Then for example, it's Br. Let's consider about the Br. Then this Br will attack here because this nitrogen is cationic species, electron deficient. So now it will come, it will open. So what will be the intermediate expected? The intermediate is that this lone pair, this is the Br and this is NO2. In next step, what is expected? It will come here, it will push, it will leave, and ultimately the product will be there with X equal to Br or Cl, whatever, depending on the acid. And interesting thing is NO2 minus is the leaving group here. Okay, so that is the reason why urea is used, because urea helps to consume the NO2 minus. Fine. Now let's discuss the last example. It is an interesting, these two examples are very interesting. Why? See, if you react to sulfuric acid in 20% sulfur trioxide, constant sulfuric acid and mercury sulfate, it results in 3-sulfonation. See the problem. As I told, aromatic electrophilic substitution generally 4 position, fine, but this is the exception. Now I'll explain why. That's why I told generally. Frankly speaking, the role of this mercury 2+, which is acting as a catalytic amount, I don't know. I haven't found. So I don't know. So what happens actually? This SO3 or sulfuric acid, what can do? See, you have this pyridine N-oxide. So this is the N-oxide. So you have, if you have proton, then there is a chance of protonation, as I described here. Fine, OH formation. Another thing, there is a sulfur trioxide. So it could be attacked. This, so a bond will form with sulfur trioxide and ultimately it will result in this. So this is the positive charge. Now see, this will act as a simple like this, will electron withdrawing effect. This, sorry, not this, like this. So ultimately what will happen? So if it acts as an electron withdrawing substituent like pyridine, so consequently it is metareacting. So that is the reason why metareacting. But why you get here para substitution? Because reactivity, this NO2 introduced the reactivity here. That's why attack happened here. But here no substitution is there. Such kind of reaction happens here. Please don't be confused between this and this. This is a simple pyridine oxide. They are substituted. So that is the reason sulfonation happens here. Okay. So if you use some removal reagent of this like PPH3, PCl3 or CCl2, this is a carbene. What happens? This oxygen is removed. Anything means I'm telling, not exactly for this. This is a removal reagent. Depending on the situation, you have to use. So ultimately, you can get the substituted derivative. This is completely my opinion. I haven't found in the book, but I want to give you the message that the methodology is possible. Means this PPH3 will be converted into. Finally, this is the oxygen will be formed double bond. Here also phosphorus oxychloride, and this carbene will be converted into carbonyl chloride or phosgene. So this is. So ultimately this. But interesting point is the fourth one. How this reaction happens. So let's discuss. See, let me draw it here. It will be easier for you to understand. So this is a pyridine N-oxide and another with that acetic anhydride. How acetic anhydride looks like? This is the acetic anhydride looks like. See, this oxygen is pretty much nucleophilic. So what happened? It will attack here. Okay. So it will go push and will leave. So what is the consequence? O, CO, CH3. And here acetate act as a leaving group. This plus. Fine. Better to draw it in this way. Another way. This. Fine. See, the electron density of this oxygen is somehow delocalized here, because if you see the canonical form, so this is the nitrogen having a plus charge, O minus CH3. This. Okay, what I want to mean that the electron density on this oxygen is reduced because of this carbonyl. Got it? Fine. Secondly, this thing you may consider as a protonated imine, like carbonyl. So nucleophilic attack can happen at this position very easily. Okay, so this is the thing. That's why it will act as a nucleophile and attack, it will open up. So ultimately, what will be the product? This is the OCOCH3. Plus charge is neutralized, so this is the hydrogen, and this is OCOCH3. Fine. Now, see, this aromaticity is destroyed, so this could be removed. Okay, so this could be removed, and another thing is that second step is hydrolysis. So it can remove in this stage at protonated form, means protonation on this or this. I will explain. This OCH3, this is the hydrogen, this is the OCOCH3. This, fine. This is the plus charge here. So protonation can happen here, and it can act as a leaving group. It can leave one point. Second, it could be even hydrolyzed to, because acid is there, to the corresponding OH. No, ultimate both case same, means and next step it will be protonated, so it become a good leaving group. So it leaves, ultimately this acetic acid or water whatever leaves, and ultimately this proton also leaves, and aromaticity is gained. So that is the message I want to give you. This. So it is a ester of pyridine derivative, but it doesn't remain in this form. It also hydrolyzes. Why? Because see, it's an electron deficient nucleus, and if you look at this molecule carefully little, this is OCOCH3, this, fine. So there is proton, so expected protonation can happen here also. So this oxygen lone pair delocalize this side, means in this way, along with this side also in this way. So both possible. What do I mean? Mean that this ester is not a stable molecule. So what happens? Water can attack and hydrolyze. So it will attack here, it will come back, it will leave. So whatever final product is this one, in 2-hydroxypyridine. Okay. So this is the overall discussion of this problem. So okay, let's continue the discussion. So in previous example I have shown just N-oxide treated with anhydride. Now let's take this methyl version and treat what is the product. This. So how to explain this? There is a easier way, means, but I believe that's wrong based on the tracer study. Okay, let me explain everything. First, what is expected, that it will be converted into acetyl derivative, OCOCH3. Fine. There is a methyl. Let's draw in this way. In next step, in medium, there is CH3COO minus. Okay. So that O minus you can expect will attack here. It will come here. Sorry, there must be nitrogen. Let's draw it in this way. This. So it will come here. So what will be the product here in this way? So this will result in double bond CH2, this NO AC. Fine. This. Sorry. This. Now, in next step, see, this is actually an electron deficient species. Why? Because that it attached to a nitrogen and that attached to a good leaving group. That's why what happened? So in the reaction medium there is acetic acid. So what can happen? From that acetate anion can further attack here, it can come here and it can leave. So ultimately what is the product? But the product is same. Then similarly, so this CH2 will attach to COCH3 and this is a simple pyridine derivative, but this is not the, you can explain, this is logically right, but another experiment doesn't suggest this pathway. It is actually a radical pathway. I will explain how. Instead of that, if you take simple this derivative, means if you say take the radio level, means this oxygen is 18 O18, but this is 16. Ultimately what we get? We get both, means CH2 OCOCH3. This is both labeled, and another product we get CH2 OCOCH3. Only one level. So this is the 16, this is the 18. Question: if this mechanism is followed, we expect all would have been 18, but it is not. Then question: how? Actually, the thing is that this is 16, this oxygen is 16, rest are all 18. So this can be broken in a homolytically. So what it will result? This nitrogen with a radical and CH2, sorry, this. Now what can happen? That this breakage in medium, there is this radical, or means from here also radical generation possible. Similarly, mixed radical. So radical will abstract the proton. What do I mean? This is CH3, this is the radical. So this radical will attach this, it will come this. So what will be the product? This is nitrogen, this and this. This is CH2 O COCH3. Fine. This is. Now question: this radical could be 16, could be 18, both possible. That is the reason here 16 and 18 both are possible. So actually this is a radical mechanism, but you don't need to always keep the mechanism because this may not ask. But question MCQ could be constructed, what will be the product, and this could be the one choice. Okay, so please keep. I believe it. If the second path seems to be very difficult, you can remember the first path, because tracer study generally not provided. So don't get tense that that is the first way, is little easier to keep the process in mind. But I have given you the exact information, otherwise you may confuse that, sir, in some books it is written in this way. So that is the reason. Now let's discuss about the last two problems. When you use thiamine chloride, it provides both 2 substituted as well as 4 substituted. But when you use PCl5, it results in only 4 substituted. So this is the product. Question: how? So let's discuss how this reaction happens. So if you react this with SOCl2, SOCl2 looks like this. So it will attack here, it will go, come back, it will leave. So what will be the product? So this is Cl. Fine. N-oxide, this is the plus charge. Now in next there is a chloride anion. Okay. So what can happen? So actually you can consider this could be a canonical form, means it can take electron and it can create the SOCl. So positive charge should come here, one canonical form, plus charge is neutralized. Another canonical form you may draw, that it can come here, so positive charge will come here. So this is the nitrogen OSOCl. Fine. This. Now see, this position, this ortho and para both are electrophilic, positive charge is there. That is the reason chlorine can attack para position or chlorine can attack ortho position, ultimately to result in both ortho and para. Okay. But when you use PCl5, what is the problem? Actually, if you read think PCl5 remains in a combination, that is PCl4 plus the formal positive charge is on phosphorus. Another thing, PCl6 minus. This doesn't react, so this reacts. So what happened? The O minus reacts O minus, pyridine N-oxide attacks here. So ultimately what will be the product in this way? If I draw, so this is the N plus O P Cl. Fine. This along with actually PCl6 is there, but this is the chlorine adapt of this. So we can consider this as PCl5 plus Cl minus. Actually the Cl minus is stabilized in this way, better to say. Please. So what happens? This Cl minus will attack here. Logically both position possible. Similar thing. Both position possible. But it exclusively attacks here. Why? See, because this group is a bulky group. So this is a bulky group. Consequently, what happens? Attacking this ortho position, accessing this ortho position is difficult, steric repulsion. So para is there, that's why chlorine attacks para position. So what happens? So NOPCl4. There is hydrogen, there is Cl. So the structure is this in this way. In next step, what happens? In next step, this hydrogen is abstracted. So what happens? It will come here, it will come here, and it will leave. Same thing is applicable for this also. Okay. So after chlorine and hydrogen attachment, similar aromaticity gaining process. So it leaves, and what it result? It result the 4-chloro-derivative. Okay. So this is the overall discussion for this problem. So we have learned a lot of chemistry. I believe sometimes it's very boring and difficult to learn all of this, but since this chemistry is very higher for master standard or NET gate thing, you should learn, because this N-oxide is a very important topic. I believe you must learn. So what we have learned today? We have learned today about different reaction of pyridine N-oxide to prepare different derivatives like meta, ortho as well as para, and finally preparation of chloro derivative directly from this N-oxide derivative. Even there are 2-hydroxy pyridine this thing from the pyridine N-oxide reagent. So this is the overall discussion. Thank you everyone for watching this video. If you really like my teaching, I request you please help me to grow my channel. First of all, subscribe my channel Chemistry the Mystery of Molecule, and please press the bell icon to get the notification of every single video I upload. Secondly, share this video among your friends so that many people could be benefited and it will help my channel to grow. And another thing, many people don't know that I am teaching. If you really think I am good, then recommend them. They will also enjoy the hard work of mine. And most importantly, please like the video and make some good comment, because it creates a lots of satisfaction for me. I have to do a lots of hard work for this. So thank you. But if you think some modification is essential, please feel free to mention in the comment box. Any criticism is welcome, but I request you please mention how to overcome it. So thank you again. Stay happy, stay blessed. See you in my next video.